All right, next up in our list of special discrete random variables, we have the multinomial distribution. And you might realize a similarity with the name of this distribution. The nomial part is familiar. In fact, it was a part of the name of our first special discrete random variable, the binomial, right? Now, when you think of the prefix multi, compared to bi, bi is implying a binary situation. So in the binomial experiment, each outcome would be one of two possibilities, right? Success or failure. The multi is implying that, well, there could be more, right? So let's write down a couple key facts about the multinomial distribution and then see what kind of results we can develop for this, right? So this distribution arises from an extension to the binomial experiment where each trial may result in k greater than or equal to 2 possible outcomes, right? And we include the 2 because if you're only 2, then it turns out the results that we um, develop for the multinomial reduces back to the binomial case, right? So it's not like separate and apart, it's a part of. So that's why we're saying the multinomial now, not only does it allow for 2, but it allows for more than 2 possible outcomes, right? So here are some of the key characteristics of this multinomial type of experiment, right? So the first one will be very familiar. We have n independent trials, right? Much like the binomial. But now each trial produces exactly one of the events, and we'll just call them, let's say, so instead, previously we had like success and failure, but now we have possibly a lot more. So I'm not going to use like S and F. I'm just going to say like event 1, so E1, E2, dot, 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 up to E sub K, right? Right. And again, what this means is that these events essentially form a partition of the sample space. So remember what a partition means. It means that the events are mutually exclusive. So mutually exclusive, right? It means they can't happen together. And so that they cover all the possibilities, we say that they are exhaustive, right? So one and only one of these events must occur on each trial. And then, well, now here's the probability part. Each of these events will have their own probability of occurring. So on each trial, event J, so EJ, don't need a comma there, so EJ occurs with probability P sub J, right? So we're going to use little p, just like how there was a little p in the binomial, but now each event will have its own probability of occurring, right? And what this means right away, so using our properties of our PDF, or you could say one of our axioms of probability, this implies that P sub 1 plus P sub 2 plus dot 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 plus P sub k, that has to be equal to 1. Why? Because again, we're saying that these events are, they could be many of them, right? But these are the only ones that can happen, and they happen each with their own probability. Hence, all those probabilities have to add up to 1, right? Okay, so that's kind of the experiment. Now, what are the random variables? Now, the thing about the multinomial is you're not just going to have one random variable. You actually have multiple random variables because you're going to be counting this. So we're going to have x1, and this will count the number of our n trials, so number of trials in which E1 occurs, right? So out of the n independent trials that we're going to conduct, how many of them end up with event 1, right? And that count is going to be representing or represented by x1. And then we're going to let x2, as you might expect, be the number of trials in which E2 occurs. And in general, x sub k is going to represent the number of trials in which E sub k occurs, right? So there are dot dot dots all there, right? So right, it's not just one random variable now, but it's multiple ones, right? And again, they're counting, each of them will count the occurrence of a specific event. And that event occurs with a constant probability. In this case, E1 occurs with the probability of P1, E2 occurs with the probability P2, and so forth. All right? So now, what's sort of interesting about this, since there are multiple variables here, you can actually think of this collection of xi's or xk's, you can think of that as a vector, right? Which is really interesting. So now you could say, like, I'll use my vector notation and think of it like this. So it's a vector where the first variable counts the number of times the first event occurs. And then your second component in your vector counts the number of times that event occurs. And then you go up to x sub k. So if you remember your facts from linear algebra, this is actually now a vector in Rk. K-dimensional vector space that now represents random vectors, or I should say random components of a vector. And then if we're using the vector notation for the random variables, why not use a vector notation for the p's to say, okay, yeah, let's just collect them and have them organized in the same manner. So have a vector that holds the probability of all these different events occurring. So P1 there, P2 there, dot, 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 PK there. Again, this would be a vector in Rk. Now, with the understanding of this property, right? So we still have to satisfy our probability axioms, right? So each of the, well, in fact, let me say it like this first. So each pi is between 0 and 1, and their summation over all k is equal to 1. So basically just kind of restating this. So yeah, it's kind of interesting now that you can think of this as a random vector. I mean, how cool is that, right? Okay, so that's one notation that we can use. Now, when you think about all the previous notations that we have, we had like a letter B for the binomial, or a NB for the negative binomial, and so forth. Well, what we can do is we can say that this vector x follows the multinomial, so we can use the M. So we can say this is multinomial, and there is still a fixed number of trials. It's still n, right? So we can use that n there, but then now for the p, it would have to be the vector p, like this, right? Now we can still refer to these as parameters of our multinomial distribution, now in this sort of vector form. So it looks very similar to the notation that we use for the binomial, but the big difference there, in the binomial case, it was one variable. Now there are multiple variables, all right? Okay, so next up we have to discuss, well, okay, so what is the PDF of this whole thing? Well, it's not difficult to see where this comes from. Again, it's just an extension of the binomial formula. Now, in our counting techniques, we looked at combinations and permutations. We didn't really focus on multinomial coefficients, so like the C's are like your binomial coefficients. Now there are multinomial coefficients, which are just an extension of the binomial ones, and that's what we will utilize now. But I'm not going to give you like a special notation for these coefficients. I'm just going to state them in terms of factorials. So that way we see it and we know exactly what it means, right? Okay, so the probability so the probability that our vector x takes on a particular value. Now that value is also going to be a vector, right? So a particular value, and that value, so it's little x, but it will be a vector. And so it's basically little x1, little x2, dot, 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 little xk, so little m cubed, right? So that's our vector of essentially possible values for each of the events, or I should say random variables. So we're still going to use our little f notation for this, right? So it will be f, but again, this will be now in sort of this vector form. And so here's the formula now for the multinomial coefficients. Usually, well, we still have an n factorial in the numerator. That's convenient. But what changes now, instead of having like an x factorial and an n minus x factorial, because there are so many other possibilities, it ends up looking like this. Simply x1 factorial, x2 factorial times dot 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 xk factorial, right? So these are the specific numbers to say, okay, how many of event 1, how many of event 2, how many of event k. So those values are here in the denominator. And now what about the p's? Well, if we want x1 number of event 1 to occur, and they each occur with probability p1, and they're independent, you're going to end up having p to the power x1, or sorry, p1 to the power x1, and then times p2 to the power x2, and then times dot 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 p sub k to the power x sub k, right? There is no p and 1 minus p, right? Because that the rest of the probability doesn't get distributed to just one other variable. There are other possibilities here, right? And we know that all the p's have to add up to 1, so it covers all the possibilities, and it's just saying you have x1 of event 1, x2 of event 2, and so on up to xk of event k. So this is the probability distribution function for the multinomial distribution, right? And the only requirement is this. So like what does the sample space look like? Well, like I said, the sample space is now it's really a vector space, if you want to say it that way. But we can still state what are the possible values of the x sub k's. For sure, they all have to be numbers from 0 to n, right? Because again, we're only doing we're only performing n trials. So each x sub k can take on values 0, 1, 2, dot, 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 up to n. But not only that, because they're mutually exclusive and exhaustive, if you take each of the possible x values, sum them up, you have to get the total number of trials that you've conducted, right? So the other requirement is that x1 plus x2 plus dot 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 plus x sub k, all the number of event 1 that we've observed and event 2 and event k, they have to total up the number of trials that we performed, right? So again, it's still a discrete sample space, but it's now in this sort of vector form. So it's essentially the components of the vector from our observation, right? So however many we observe for x1, x2, all the way up to x sub k, then those number of observations have to total our number of trials. All right. Okay, so all this talk about vectors and so forth. Well, let's take a look at an example, right? So we're going to take a look at an example, and so I'm not really going to put a story behind it, but let's just say we have a population, let's say in a particular city, and the people in that city, they're categorized into 3 categories. I'm just going to call them category 1, category A, B, and C, right? So we have a population, right? And here are the categories A, B, C. And here is the percentage or the probability of a person being in one of these 3 categories. And these are, again, mutually exclusive and exhaustive. So here are the probabilities, right? So these would be our little p's. So here are our probabilities. So let's say 20% of our population is in category A. And let's say 15% in category B, and then the remaining 65% are in category C. And what we're going to do is randomly choose 12 people from this population. So here's our experiment. We're going to choose n equals 12 people from this population, right? And then the question is, and then so we're gonna do two questions. So part A is this: what is the probability? So what is the probability that we observe, or our trial yields, let's say 3A, so 3 from category A, 2 from category B, and then 7 from category C, right? And again, this is the whole idea where we have more than 2 possibilities. So I just figured let's do one with 3, right? So, it doesn't get too tedious in terms of the numbers and the different possibilities, but it does give you the sense that this is more than the binomial, right? I guess technically you could call this a trinomial since there are 3 possibilities, right? So that's our question, right? Well, let's write down the PDF. Now, do you have to use that vector notation? No, you don't. As long as you recognize that, yes, these are multiple variables that you are now analyzing, right? So you don't have to use your vector notation, but know that, yes, this is a vector here. But let's set it up. So we have our 12 number of trials, right? And so we're going to have 12 factorial there. And then in the bottom now, so again, what I'm writing down is the general formula. So it's going to be x1 factorial. And the x1 for us, and I'll write it over here. So x1 will be the number of people in category A. So in fact, let me write this uppercase. So x1 is the number of people in A, and then let's say x2 is the number of people in B, and then finally x3 is the number of people in C, right? So yeah, so we'll have a number here for x1 and then factorial, and then we'll have a number here for x2 factorial, and then a number here for x3 factorial. And then as far as the probabilities now, so it's going to be 0.2 raised to whatever number x1 is. So whatever number we're trying to find the occurrences of that category A, and that number will be my exponent there. And then for category B, it's going to be times 0.15 to the power x2. And then for category C, it's going to be 0.65 to the power x3. All right. So so now for this particular question, what it's asking is, what is the probability of observing 3, 2, 7 in that order? So like when you write it like this, there is kind of that vector notation, right? So you're interpreting it saying, okay, I observe 3 occurrences in the first category, category A, 2 in the second, that's category B, and then 7 in the third, category C. So now we're going to plug in the numbers x1, x2, x3. So we have our 2 factorial divided by 3 factorial times 2 factorial times 7 factorial. And then we're going to have 0.2 to the third power times, maybe I'll put these in parentheses, and then 0.15 to the second power, and then 0.65 to the seventh power, right? So yeah, at this point, we turn to our calculator and we will get a probability of 0.0699, right? So just under a 7% chance that if we pull 12 random people from this population, we will observe exactly 3 in category A, 2 in category B, and 7 in category C. All right. Let's do another part. So again, what is the probability? So what is the probability that we observe? Now let's say 4 in category A, and let's say none, right? 0 in category B, and then let's say, well, not let's say, well, that would mean 8, right, in category C. Right? What is that probability? Well, in that case, our vector now would be 4, 0, 8. And that's where the order is important, right? Because we know that, just like in a vector, you can't just switch the components around and get the same vector. No, you change it around, you change the occurrence, you change the event, right? So in this case, it will be 4, 0, 8. So we'll still have the 12 factorial in the numerator, but now we're going to have 4 factorial times 0 factorial times 8 factorial, and then we're going to have the 0.2 to the 4th power, and then 0.15, now that's going to be to the 0th power, so that's going to be equal to 1, and then finally the 0.65 to the 8th power, right? So the numbers whose factorial we take in the denominator, they have to add up to our n, which is the number in the numerator, right, whose factorial we're taking. Similarly, the exponents here have to add up to our n, right? And in this case, ends up even smaller than this probability. It's 0.0252, right? So just about a 2.5% chance that, again, in this scenario, we will observe 4 individuals in category A, 0 individuals in category B, and 8 individuals in category C. Now let's look at part C here. Now again, just to show you that the binomial in this case, again, the binomial is a special case of the multinomial, right? So what if we wanted this probability? So what is the probability, right, of at most one person from category A? So of at most one person from category A, right? So here, the only restriction is, yeah, we want to have at most one person in category A. That means we don't care what happens in the other category. Well, in some sense we do, right? So in this case, it's basically we're defining observing someone from category A as a success, and if we don't, then it's a failure. So this is actually going back to the binomial now, And essentially, this is how it's going to be set up. So the probability that we observe at most in the first category, one person, so like this, well, we know what at most one means. That's the probability that our x1 is either equal to 0 or equal to 1. Well, so the probability of getting no individuals from category A, so that would mean you'd have your 12 factorial in the numerator, and then what you'd have is nothing from category A, and then everything else from from B and C. So you kind of put the B and C together and say, okay, well, that's your failure. So basically this, right? And then when you think about the probabilities, it would be your 0.2 raised to the power 0 power. Your 0.2 raised to the 0th power, and then that's multiplied by, well, the probability that you're not in category A is 0.8, right? And you want all 12 to not be in category A, right? So you can see this is our binomial formula, and it works out. So it basically comes out to be 0.8 to the 12th power, and if we round that to 4 decimal places, we get 0.0687, right? So that's the probability that we'll get. Well, actually, what I should do is, yeah, this is not equal to that. This is just the probability that it's 0. So let's add the probability that x is equal to 1. So do this. There we go. So the probability that we get exactly 1 from category A, so that's 12 factorial. We now have 1 factorial, that's from category A, which means the remaining 11 would be in either B or C, right? But we're not putting any restrictions on it. We're just saying it's either A or not A. And then your probabilities are like this: 0.2 to the first power, and then times 0.8 to the 11th power, right? So now let's write down those two probabilities and add them. So as I said earlier, that one, the 0.8 to the 12th power, is 0.0687, and then plus this. So this ends up being 12 times 0.2 times 0.8 to the 11th power, and that gives us 0.2061, and then our final probability is 0.2748, right? So roughly 27.5% of the time we will observe at most one person in category A, right? So that's the multinomial case. As far as a few examples. Now, let's kind of wrap this up by stating the formulas for expected values and variances. Now, since there are multiple random variables, again, the number of occurrences for event 1, the number of occurrences for event 2, they each have their own separate mean and variance, right? So I'll state it like this: the expected value of the ith variable, that's equal to your n times your p sub I. And this makes sense, right? If you're going to perform the experiment n number of times, and this particular random variable has a probability of pi right, occurring, then you'd expect roughly that proportion of your number of experiments to end up occurring in that particular event. And then the variance, same variance as it is for the binomial. It's your n and then times pi times 1 minus pi, right? So it again, this just shows you the close relationship between the binomial and the multinomial. It's just that now you have multiple of these variables. All right. So there you go, the multinomial, extension of the binomial, and it has a lot of really good applications to it, right? So I will see you in the next video.